Imagine a dead star, a white dwarf. It's about the size of Earth, but it holds the mass of our Sun. A single teaspoon of its material would weigh about 5 tons. It's one of the densest objects in the known universe, and for billions of years it just sits there, slowly cooling in the quiet darkness of space, perfectly stable, perfectly quiet. But under certain conditions, something ignites deep inside its core, carbon begins to fuse. In any normal star, this would be fine. The star would expand, cool itself down, and return to balance. But a white dwarf cannot expand. It cannot regulate. The temperature climbs, the burning accelerates, and within seconds, a thermonuclear inferno consumes the entire object. The star doesn't just die, it ceases to exist. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with something that might seem obvious, but is actually one of the most extraordinary balancing acts in all of nature. Stars burn. You know that. Everyone knows that. But what most people don't appreciate is how delicate that burning really is. A star is not just a ball of fire sitting out in space, doing its thing without consequence. A star is a battlefield. Every second of every day for billions of years, two titanic forces are fighting inside it. And the star survives only because neither side wins. On one side, you have gravity. Gravity is relentless. It never stops. It never weakens. It never takes a break. And inside a star, gravity is trying to do one simple thing: crush everything inward, pull every atom, every particle of gas toward the center. Compress the star into the smallest, densest object it can become. A star like our Sun contains roughly 332,000 times the mass of Earth. All of that mass is pulling on itself. The weight of the outer layers pressing down on the core creates a pressure at the center of the Sun of about 265 billion times the atmospheric pressure here on Earth's surface. That is an almost incomprehensible amount of force, all directed inward, all trying to squeeze the Sun into something unimaginably small. If gravity were the only force at work, the star would collapse in minutes. The entire Sun would crumple inward like a building with no supports, falling in on itself until the material physically could not be compressed any further. But gravity doesn't get to win, because something is pushing back. Deep in the core, where temperatures reach about 15 million degrees Celsius, and the pressure is beyond anything we could ever replicate on Earth, something extraordinary is happening. Hydrogen nuclei, which are just individual protons, are being slammed into each other with such speed and force that they overcome their natural electromagnetic repulsion and fuse together. 4 hydrogen nuclei combine to form one helium nucleus through a series of steps called the proton-proton chain. But here's the critical detail. The helium nucleus that comes out of this process weighs slightly less than the 4 hydrogen nuclei that went in. About 0.7% of the original mass is missing. That mass hasn't disappeared. It has been converted into energy, following Einstein's famous relationship between mass and energy. And even though 0.7% sounds like a tiny fraction, when you're talking about the core of a star, where roughly 600 million tons of hydrogen are being converted into helium every single second, that tiny fraction adds up to a monstrous output. The sun releases more energy in 1 second than all of human civilization has produced in its entire history. Every second, continuously, for billions of years. This energy radiates outward from the core. It heats the surrounding gas. It creates pressure that pushes outward, directly opposing gravity's inward pull. And when these two forces, gravity pulling in and fusion energy pushing out, are exactly in balance, the star reaches a state that physicists call hydrostatic equilibrium. Hydrostatic equilibrium is one of the most important concepts in all of astrophysics. It is the reason stars exist in a stable form. It is the reason the sun doesn't collapse under its own weight, and it is the reason the sun doesn't blow itself apart from all the energy being generated in its core. The two forces balance each other perfectly. Gravity provides just enough compression to keep the core hot and dense enough for fusion. Fusion provides just enough energy to keep gravity from collapsing the star. It is a perfect standoff. A cosmic tug-of-war where neither side ever gains the upper hand. But here is what makes this balance truly remarkable. It is self-correcting. This is the detail that matters most for our story tonight. A normal star has a built-in thermostat, and it works beautifully. Here is how it works. Imagine something happens in the core that causes the fusion rate to increase slightly. Maybe a small region gets a bit hotter than usual. Maybe a pocket of fuel is slightly denser than the surrounding material. Whatever the cause, more fusion reactions occur and more energy is released. That extra energy heats the surrounding gas. And here's the key. When normal gas gets hotter, it expands. This is basic thermodynamics. Heat a gas and it pushes outward, taking up more volume. So the core expands slightly. But when the core expands, the material spreads out. The density drops. The particles are farther apart. They collide less frequently. The fusion rate decreases. Less energy is produced. The core cools slightly and contracts back toward its original size. Balance is restored. Now imagine the opposite. Something causes the fusion rate to drop. Less energy is produced. The core cools slightly. When the gas cools, it contracts. Gravity pulls it inward. The material becomes denser. Particles are closer together. They collide more often. The fusion rate increases again. More energy is produced. The core heats up and expands back to its original state. Once again, balance is restored. This feedback loop is incredibly powerful. It means that a normal star is self-regulating. If it gets too hot, it expands and cools itself down. If it gets too cool, it contracts and heats itself up. It is like a thermostat in your house. If the temperature drops too low, the heater kicks on. If the temperature climbs too high, the heater shuts off. The temperature stays within a narrow range because the system automatically corrects any deviation. You don't have to think about it. You don't have to intervene. The system takes care of itself. This stellar thermostat is the reason stars can burn steadily for billions of years. Without it, fusion would either run away, getting hotter and hotter in an unstoppable chain reaction until the star ripped itself apart, or it would fizzle out as the core cooled and compressed into a state where fusion could no longer be sustained. The thermostat prevents both extremes. It keeps the star in that delicate balance between catastrophic explosion and total collapse. And this balance holds for an almost unimaginable span of time. Our sun has been doing this for about 4.6 billion years. Every day, the fusion reactions in its core produce energy. That energy pushes outward. Gravity pulls inward. The two forces match. The sun shines steadily, producing roughly the same amount of energy today as it did a billion years ago. Not exactly the same. The sun is actually getting very slowly brighter over time, about 1% more luminous every 100 million years or so. But the changes are gradual, gentle, because the thermostat keeps everything under control. There are no sudden spikes, no catastrophic fluctuations, just a slow, steady burn that has lasted for billions of years and will continue for billions more. Think about what that means for a moment. Our sun has been burning since before the first complex life appeared on Earth. It was burning when the first fish swam in ancient seas. It was burning when dinosaurs walked the planet. It was burning when the first humans looked up at the sky and wondered what that bright light was. And through all of that time, across 4.6 billion years of continuous operation, the thermostat has kept the fusion rate stable enough for life to emerge, evolve, and eventually understand the very process that makes the sun shine. That is an extraordinary piece of self-regulation. The sun currently has enough hydrogen fuel in its core to keep fusing for roughly another 5 billion years. That sounds like a long time, and it is. Human civilization is only a few thousand years old. 5 billion years is almost incomprehensibly far in the future, but stars don't last forever. Eventually the fuel runs out, and when it does, everything changes. Here is what happens. Over billions of years, the hydrogen in the sun's core is gradually converted into helium. The core slowly fills up with helium ash, the product of all that fusion. And helium, at the temperatures and pressures inside the sun's core right now, does not fuse. It just sits there, inert, dead weight. As more and more of the core's hydrogen is consumed and replaced by helium, the active region where fusion is occurring gradually shrinks. The core is becoming clogged with waste, filling up with a byproduct it cannot use. Eventually the core runs out of hydrogen entirely. Fusion in the core stops. Now remember what was keeping the star from collapsing. It was the energy from core fusion pushing outward, balancing gravity's inward pull. When that energy source vanishes, gravity suddenly has the upper hand. The core begins to contract. There is nothing pushing back anymore, no fusion energy to resist the squeeze. As the core contracts, it gets hotter and denser. Gravitational energy is being converted into heat as the material falls inward. The layer of hydrogen immediately surrounding the dead helium core is now being compressed and heated by the contracting core beneath it. And when that hydrogen shell reaches the right temperature and pressure, something interesting happens. Fusion ignites in the shell, not in the core anymore, but in a thin layer wrapped around it. This shell burning produces enormous amounts of energy, far more than the core ever produced during its steady main sequence life. The flood of energy pours into the outer layers of the star, heating them and pushing them outward. The star begins to expand. And it doesn't expand just a little. It expands enormously. The outer layers puff out to many times their original extent. The surface stretches over a vastly larger area. And because the same amount of energy is now spread across that much bigger surface, the surface temperature actually drops. The star shifts from yellow-white to a deep, glowing red. The star has become a red giant. When our sun reaches this stage, roughly 5 billion years from now, it will swell to somewhere between 100 and 200 times its current diameter. Its outer edge will push past the orbit of Mercury. It will engulf Venus entirely. It may even reach Earth's orbit. Even if Earth is not swallowed directly, The sheer heat radiating from the bloated sun will boil away the oceans, strip the atmosphere, and scorch the surface of our planet into a barren, lifeless rock. Meanwhile, inside the red giant, the helium core continues to contract under its own weight. As it does, its temperature keeps climbing. Eventually, the helium reaches a critical threshold, roughly 100 million degrees Celsius. At that extreme temperature, helium nuclei can fuse. 3 helium nuclei combine to form 1 carbon nucleus in a process called the triple alpha process. Some of that newly forged carbon then captures another helium nucleus and becomes oxygen. The core is producing energy again, this time by fusing helium into carbon and oxygen. The star settles into a new phase of equilibrium, burning helium in the core and hydrogen in the shell around it. But helium is a less efficient fuel than hydrogen. For a star like the Sun, this helium-burning phase lasts roughly 100 million years. That sounds like a lot, but compare it to the roughly 10 billion years the star spent on the main sequence burning hydrogen. Helium burning is a brief chapter in the star's life, and the core is gradually filling up with a new kind of ash now. Carbon and oxygen, the products of helium fusion. And here's where the story takes a crucial turn. In a star like the Sun, the carbon and oxygen sitting in the core will never fuse. Carbon fusion requires temperatures of at least 500 million degrees Celsius. Oxygen fusion demands even higher temperatures still. For a star with the mass of our Sun, gravity simply cannot compress the core hard enough to reach those extremes. The temperature needed for carbon ignition is never achieved. The fuel is there. Carbon and oxygen are sitting right there in the core, packed together under tremendous pressure. But the match is not hot enough to light them. It is like having a pile of logs soaked in lighter fluid, but no flame that burns hot enough to set them alight. The potential energy is enormous, but it remains locked away, unreachable, untapped. Without a new fusion source, the core has nothing left to fight gravity with. It contracts again, but this time, the outer layers of the star cannot hold on. The star is simply not massive enough to keep its extended atmosphere gravitationally bound during all this upheaval. Over the course of tens of thousands of years, the red giant sheds its outer layers into space. Great shells of gas drift outward, expanding into the surrounding void. They are lit from within by the fierce ultraviolet radiation streaming from the exposed core that sits at the center. We call these expanding structures planetary nebulae, though they have absolutely nothing to do with planets. The name is a historical accident from early telescope users who thought these fuzzy, round objects looked like the disks of distant planets. Some of these planetary nebulae are among the most beautiful objects astronomers have ever photographed. The Ring Nebula in the constellation Lyra, the Cat's Eye Nebula in Draco, the Helix Nebula in Aquarius. They glow in vivid colors, reds and blues and greens, as different elements in the expanding gas are ionized and excited by the intense radiation from the stellar remnant at their center. But they are temporary. They last only about 10,000 to 20,000 years before they dissipate into the surrounding interstellar medium. Their material mixing back into the vast clouds of gas and dust that will one day be recycled into future generations of stars and planets. And at the center of each fading nebula sits the object we have been building toward all this time, the exposed core, the spent heart of a dead star, a white dwarf. A white dwarf is what remains when a star like the Sun has burned through every fuel source it can possibly access. It is the carbon and oxygen core, the accumulated ash of billions of years of nuclear fusion, now laid bare and left alone in the darkness of space. And it is one of the strangest, most extreme objects in the known universe. A typical white dwarf contains roughly half to about 80% the mass of our Sun. All of that mass is packed into an object approximately the size of Earth. Think about that for a moment. A star's worth of material compressed into a volume the size of a single rocky planet. The density is staggering. A cubic centimeter of white dwarf material, a volume roughly the size of a sugar cube, weighs about 1 metric ton. A teaspoon of it, if you could somehow scoop it up and bring it to Earth's surface, would weigh about 5 tons. You could not lift it. You could not place it on a table. It would crash through whatever surface you set it on and keep going. To put this density in perspective, the average density of surface rock on Earth is about 2.5 to 3 grams per cubic centimeter. The density of iron is about 8 grams per cubic centimeter. The density of white dwarf material is about 1 million grams per cubic centimeter. That is roughly 130,000 times denser than solid iron. If you could somehow collect a bowling ball-sized sphere of white dwarf material, it would weigh approximately 5,000 metric tons. An object small enough to hold in 2 hands, weighing about as much as a large naval destroyer. The surface temperature of a newly formed white dwarf can exceed 100,000 degrees Celsius. That is nearly 20 times hotter than the surface of our Sun. These objects are intensely, blindingly hot when they first emerge from the dissipating planetary nebula. They glow with a fierce, blue-white light, which is how they earned the name white dwarf. But here's the critical detail: they are producing no new energy. There was no fusion happening inside them, no hydrogen burning, no helium burning, nothing. The heat they radiate is leftover thermal energy from the star's earlier life, residual warmth stored in the incredibly dense material. The white dwarf is simply bleeding that stored heat into space, slowly, patiently, over eons. And it does so with extraordinary slowness. Because the material is so dense and the surface area is so small relative to the amount of heat stored inside, a white dwarf cools very gradually over billions of years. Its surface temperature drops from hundreds of thousands of degrees to tens of thousands, then to thousands, eventually to hundreds. The oldest white dwarfs in our galaxy, those that formed in the earliest epochs of the Milky Way's history, have been cooling for more than 10 billion years, and they are still warm enough to glow faintly. In theory, given enough time, a white dwarf would eventually cool completely, becoming a cold, dark, invisible object called a black dwarf. But the universe is only about 13.8 billion years old. That is nowhere near long enough for any white dwarf to have finished cooling. Every white dwarf that has ever formed in the entire history of the cosmos is still out there right now, still glowing, still releasing its stored heat into the void. There are a lot of them. Astronomers estimate that roughly 97% of all stars in the Milky Way will eventually end their lives as white dwarfs. Only the most massive stars, those born with roughly 8 or more times the mass of our Sun, die in violent supernova explosions and leave behind neutron stars or black holes. The vast majority of stars in the universe are not that massive. Most are modest, similar in size to the Sun or smaller, and they will all walk the same path. Main sequence: red giant, planetary nebula, white dwarf. Our galaxy alone contains an estimated 10 billion or more white dwarfs right now, quietly fading in the darkness. The most famous white dwarf is probably Sirius B, the companion star to Sirius, the brightest star in the night sky. Sirius B was one of the first white dwarfs ever identified. In 1844, the German astronomer Friedrich Bessel noticed that Sirius was wobbling slightly as it traveled across the sky. The wobble was subtle but unmistakable. Something massive but invisible was orbiting Sirius, tugging it back and forth with its gravity. Bessel concluded that a hidden companion star must exist, too faint to be seen directly, but heavy enough to make the bright primary star sway. 18 years later, in 1862, the American telescope maker Alvin Graham Clark pointed a powerful new refractor at Sirius and spotted the faint companion star directly for the first time. It was incredibly dim, barely visible next to the blinding glare of its partner. Subsequent measurements revealed something baffling. Sirius B had roughly the mass of our Sun. That much was clear from the gravitational wobble it imposed on Sirius. But it was extraordinarily faint. When astronomers measured its temperature, they found that Sirius B was actually very hot, hotter even than the surface of the Sun. This created a paradox. If Sirius B was that hot, it should have been buried. The only way an object could be both extremely hot and extremely dim was if it was incredibly small. A small surface area radiates less total light, even at very high temperatures. The calculations showed that Sirius B had to be roughly the size of Earth. A star carrying the mass of the Sun compressed into a volume no larger than a rocky planet. When this result was first announced, many astronomers simply refused to believe it. The densities implied were so extreme, so far beyond any material known to science, that the whole idea seemed physically impossible. How could matter be squeezed that tightly? What conceivable force could hold such an object up against its own crushing gravity? If there was no fusion burning inside it, no energy source generating outward pressure, why didn't it simply collapse further? What was stopping it? These questions would take decades to answer, and the answers would come from one of the most unexpected places in all of physics. Not from astronomy, not from thermodynamics, from quantum mechanics. Because it turns out that the matter inside a white dwarf is fundamentally different from the gas inside a normal star. It obeys different rules, it responds to different forces, and the force that holds a white dwarf up against gravity has nothing to do with temperature, nothing to do with fusion, nothing to do with any process that operates inside a living star. It is a quantum mechanical effect so strange, so counterintuitive, that when it was first proposed, some of the greatest physicists of the age struggled to accept it. And here is the terrible irony at the heart of tonight's story. That same force, the very thing that makes a white dwarf stable and allows it to sit quietly cooling for billions of years, is also the thing that makes it catastrophically vulnerable. Because the stellar thermostat that keeps normal stars alive, that beautiful self-correcting feedback loop between heat and expansion, does not work inside a white dwarf. The thermostat is broken. And when ignition happens inside an object where the thermostat is broken, the outcome is not a gentle correction. The outcome is not a return to balance. The outcome is total, irreversible annihilation. The kind of explosion that can briefly outshine an entire galaxy. But to understand why, to understand how the same property could be both shield and fatal weakness, we first need to understand what holds a white dwarf up. We need to understand what makes its matter so profoundly different from the gas inside any normal star. And that will take us into one of the strangest corners of physics ever discovered, where the rules you thought you understood about how matter behaves simply stop applying. To understand what holds a white dwarf up against its own crushing weight, and more importantly, to understand why that support mechanism contains within it the seeds of absolute catastrophe, we need to step away from the scale of stars for a moment. We need to go in the opposite direction. We need to go small. Incredibly, almost unimaginably small, down to the scale of individual atoms and the particles inside them. Because the answer to how a dead star supports itself against gravity comes not from astronomy, not from thermodynamics, not from any branch of physics that deals with large objects. It comes from quantum mechanics, the science of the subatomic world. And quantum mechanics has rules that seem to violate everything common sense would suggest about how matter should behave. In our everyday lives, matter behaves predictably. If you have a box and you put a ball inside it, the ball occupies a position. You can measure that position. You can predict where the ball will be if you push it. Nothing surprising happens. Two balls can sit side by side in the box without any issue. 3 balls, 4 balls, however many you want. As long as the box is big enough, they all fit and they all behave as you would expect. But at the quantum level, at the scale of electrons and protons and neutrons, none of this works the way you would expect. Particles don't have precise positions and precise velocities at the same time. They exist in a haze of probability, smeared out across a range of possible states. You cannot pin down exactly where an electron is and exactly how fast it is moving simultaneously. This is not a limitation of our instruments. It is not a matter of needing better microscopes or more precise detectors. It is a fundamental property of reality itself. At the quantum scale, certainty has limits. This strangeness leads to a rule that has enormous consequences for the structure of matter throughout the universe. It is called the Pauli exclusion principle, named after the Austrian physicist Wolfgang Pauli, who formulated it in 1925. The principle states something deceptively simple. No two identical fermions can occupy the same quantum state at the same time and place. Let me unpack that. First, what is a fermion? Fermions are a category of subatomic particles that includes electrons, protons, and neutrons. Essentially, the particles that make up ordinary matter are fermions. There is another category called bosons, which includes particles like photons, the particles of light. Bosons play by different rules, but fermions, the building blocks of atoms, and therefore of you and me and everything we can touch, obey the Pauli exclusion principle. Second, what does quantum state mean? A quantum state is a complete description of a particle's condition. For an electron in an atom, the quantum state includes things like its energy level, its orbital shape, and a property called spin, which you can think of as the electron's orientation, though is not literally spinning in the way a top spins. Each unique combination of these properties defines a distinct quantum state. The Pauli exclusion principle says that if one electron already occupies a particular quantum state, no other electron can be in that exact same state. The position is taken, occupied, no vacancies. The second electron has to find a different state, a different energy level, a different spin, something that distinguishes it from the first. This principle is the reason atoms have the structure they do. It is the reason the periodic table exists. It is the reason chemistry works the way it does. If the Pauli exclusion principle did not exist, every electron in every atom would collapse into the lowest possible energy state. all atoms would behave the same way. There would be no chemistry, no molecules, no solid matter, no liquid water, no you, no me, no Earth, no stars. The entire complexity of the material universe rests on this one quantum mechanical rule. You cannot stack identical fermions into the same state. Now here is where this becomes relevant to white dwarfs. Remember what a white dwarf is. It is about half to 80% the mass of the Sun squeezed into a volume the size of Earth. The density is roughly 1,000,000 times that of water. The atoms inside a white dwarf are packed so tightly that their electron clouds overlap. The electrons are no longer bound to individual atoms. They are free, forming what physicists call an electron gas that pervades the entire interior of the star. And here is the problem. There are an enormous number of electrons crammed into a relatively small space. As you squeeze more and more electrons into a tighter and tighter volume, something has to give. The Pauli exclusion principle demands that no two electrons can share the same quantum state. But with so many electrons in so small a space, the low-energy quantum states fill up quickly. The electrons at the bottom have nowhere to go. They are already in the lowest available states. So as compression continues, electrons are forced into higher and higher energy states, not because they are being heated, not because energy is being added, simply because all the low energy states are already occupied, and the exclusion principle forbids doubling up. These high energy electrons are moving fast, very fast. Even if the temperature of the white dwarf were somehow reduced to absolute zero, these electrons would still be racing around at tremendous speeds because they have no choice. The low energy, slow moving states are all taken. They are forced to occupy fast, high energy states by the sheer impossibility of being in any state that is already occupied. It is like a crowded parking garage where every lower level is full. You have to keep driving upward to higher and higher floors, even if you don't want to, simply because there is nowhere else to park. These fast-moving electrons exert a pressure. They push outward against anything trying to compress them further. This pressure is called electron degeneracy pressure, and it is fundamentally different from any kind of pressure you encounter in everyday life, or even inside a normal star. In a normal star, the pressure that supports the star against gravity is thermal pressure. It comes from heat. Hot gas has particles moving fast, and those fast-moving particles push outward. The hotter the gas, the faster the particles move, the higher the pressure. Cool the gas down, and the particles slow. The pressure drops. This is why the stellar thermostat works. Temperature and pressure are linked. Change one, and you change the other. But electron degeneracy pressure does not work this way. Degeneracy pressure does not depend on temperature. It depends only on density. Specifically, it depends on how tightly the electrons are packed together. As long as the density stays the same, the degeneracy pressure stays the same, regardless of whether the material is extremely hot or stone cold. You could heat degenerate matter to 1,000,000,000 degrees, and the pressure would barely change. You could cool it to near absolute zero, and the pressure would barely change. The electrons are being held in their high energy states, not by thermal energy, but by the Pauli exclusion principle. They literally cannot drop to lower energy states, because those states are occupied. Temperature is irrelevant. The quantum mechanical prohibition does not care how hot or cold the material is. This is the crucial point. This is the detail that changes everything. And I want you to sit with this for a moment because the consequences are staggering. Inside a normal star, The thermostat works because pressure depends on temperature. If the star gets hotter, it expands. If it gets cooler, it contracts. The star self-corrects. It maintains equilibrium. But inside a white dwarf, the pressure holding the star up has nothing to do with temperature. If you heat the material inside a white dwarf, the pressure does not increase significantly. And if the pressure does not increase, the star does not expand. There is no expansion to cool things down. There is no self-correction. There is no feedback loop. The thermostat is not just malfunctioning. It does not exist. It has been replaced by something that does not respond to heat at all. The white dwarf is being held up by a quantum mechanical wall that is completely indifferent to temperature. Now think about what this means. In a normal star, if something causes the temperature to rise unexpectedly, the star expands, cools off, and returns to equilibrium. Crisis averted. The thermostat handled it. But in a white dwarf, if something causes the temperature to rise, nothing happens structurally. The star does not expand. The material does not spread out. The density does not drop. The temperature just keeps climbing. And if the source of that temperature increase is still operating, if heat continues to pour into the material, the temperature climbs further and further and further, with nothing to stop it. This is the broken thermostat. This is the fundamental vulnerability buried inside every white dwarf in the universe. The very thing that makes a white dwarf stable, electron degeneracy pressure, is also the thing that makes it unable to regulate any heating event that occurs inside it. Stability and vulnerability are the same property. The shield and the fatal weakness are one and the same. When the concept of electron degeneracy pressure was first developed in the 1920s, primarily through the work of the English physicist Ralph Fowler, it was seen as a triumph. It solved the mystery of white dwarfs. It explained how Sirius B could exist. It showed how a dead star could support itself against gravity without any fusion occurring inside it. The quantum mechanical pressure of tightly packed electrons was enough to hold the star up indefinitely. As long as the mass was not too great, the electrons could resist gravity's inward pull forever. The white dwarf would simply cool, gradually fading over billions of years, but never collapsing. But almost immediately, a young Indian astrophysicist named Chandrasekhar spotted a problem. In 1930, while travelling by steamship from India to England to begin his graduate studies at Cambridge, Chandrasekhar was working through the mathematics of white dwarf structure. He was only 19 years old, and he realised something that would change astrophysics forever. Chandrasekhar understood that electron degeneracy pressure, powerful as it is, has a limit. As a white dwarf becomes more massive, gravity becomes stronger. The electrons must be packed more tightly to generate enough degeneracy pressure to resist that stronger gravity. They are forced into even higher energy states. They move faster, but there is a cosmic speed limit. Nothing can move faster than the speed of light. As the electrons approach the speed of light, they become what physicists call relativistic. Their behavior changes. The relationship between their speed and the pressure they generate shifts. The pressure still increases with density, but it increases more slowly than gravity does. This means that beyond a certain mass, electron degeneracy pressure simply cannot keep up with gravity. No matter how tightly you pack the electrons, no matter how high their energy states, the pressure they generate is not enough to counteract the gravitational force of the overlying material. Chandrasekhar calculated this critical threshold with remarkable precision. The maximum mass a white dwarf can support through electron degeneracy pressure is approximately 1.4 times the mass of our Sun. This value is now called the Chandrasekhar limit, and it is one of the most important numbers in all of astrophysics. Below the Chandrasekhar limit, electron degeneracy pressure wins. The white dwarf is stable. It can sit there cooling for billions upon billions of years without any structural change. Gravity pushes inward. Degeneracy pressure pushes outward. Neither side can overcome the other. The star persists, slowly fading, but structurally intact. At or above the Chandrasekhar limit, gravity wins. Electron degeneracy pressure is no longer sufficient to hold the star up. The structure cannot support itself. Something has to give. When Chandrasekhar presented these findings to the astronomical community, he was met with fierce resistance. The most prominent objector was Arthur Eddington, one of the most celebrated astrophysicists of the era. Eddington found the implications of Chandrasekhar's work deeply troubling. If a white dwarf could not support itself above a certain mass, what happened to it? The mathematics suggested it would collapse without limit, shrinking to an infinitely small, infinitely dense point. This seemed absurd, even obscene. Eddington publicly attacked Chandrasekhar's conclusions, calling them a reductio ad absurdum, a result so ridiculous that it disproved the assumptions that led to it. But Chandrasekhar was right. The mathematics was sound. The physics was correct. And over the following decades, the astronomical community gradually accepted the Chandrasekhar limit as a real, physical constraint on white dwarf structure. It earned Chandrasekhar the Nobel Prize in Physics in 1983, more than half a century after his original calculation on that steamship. The Chandrasekhar limit is not just a number. It is a line in the sand. On one side, stability. On the other side, catastrophe. And the nature of that catastrophe depends on the circumstances. If a truly massive star exhausts its fuel, and its core is above the Chandrasekhar limit, electron degeneracy pressure fails, and the core collapses directly. It falls inward until the protons and electrons are crushed together, forming neutrons, and a new kind of degeneracy pressure, neutron degeneracy pressure, holds the collapse. The result is a neutron star, an object about 12 miles across but containing more mass than the Sun. If the core is even more massive, beyond about 2 to 3 solar masses, even neutron degeneracy pressure fails, and the collapse continues all the way to a black hole. But there is another path, a more insidious path, and it is the one at the heart of our story. Most white dwarfs form well below the Chandrasekhar limit. A typical white dwarf has perhaps half to about 70% the mass of the Sun. It is safely below the threshold. It should be stable forever. And if the white dwarf were alone, drifting through the void of interstellar space in complete isolation, it would be. It would simply cool for eternity. A harmless, slowly fading ember in the darkness. No threat to anything. But many white dwarfs are not alone. Stars often form in pairs, binary systems where two stars orbit each other, bound together by mutual gravity. When one star in a binary system dies and becomes a white dwarf, the other star may still be alive, still burning its fuel, still evolving. And as that companion star ages and expands, perhaps swelling into a red giant, its outer atmosphere can drift close enough to the white dwarf that the white dwarf's gravity begins to pull material from the companion's surface. This is called mass transfer, and it changes everything. Hydrogen and helium from the companion star spiral inward toward the white dwarf, forming a swirling disk of material called an accretion disk. The material in the disk gradually loses energy through friction and turbulence, and it falls onto the surface of the white dwarf. Layer by layer, the white dwarf gains mass. Not rapidly, not violently, but steadily, persistently, over millions of years. And here something dramatic happens long before the final catastrophe. As hydrogen from the companion accumulates on the white dwarf's surface, the weight of each new layer compresses the material beneath it. The base of this accreted hydrogen shell gets hotter and denser. And remember, hydrogen is the easiest element to fuse. It requires far lower temperatures and pressures than carbon or oxygen. So before the carbon core is ever in danger, the surface hydrogen reaches its own ignition point. Fusion erupts in a thin shell on the white dwarf's surface. The hydrogen burns explosively, and the energy released blows the accreted layer off the star in a brilliant flash. The white dwarf brightens by a factor of tens of thousands or even hundreds of thousands in a matter of hours. A star that was too faint to see with the naked eye suddenly appears in the sky as a bright new point of light, then fades over the following weeks. This is a classical nova. And it is not the same thing as the final explosion we are building toward. A nova is a surface event. It is a skin-deep detonation. The hydrogen shell is destroyed, but the carbon-oxygen core beneath it is completely untouched. The white dwarf survives. It is barely affected. The nova is like a sunburn on the surface of the star. Painful and dramatic, but not fatal. Not even close to fatal. The core sits there, dense and degenerate and structurally intact, completely indifferent to the fireworks happening on its skin. And then the process starts over. The companion star is still there. It is still losing mass. Hydrogen begins to accumulate on the white dwarf's surface again. Over the course of thousands to tens of thousands of years, the layer builds back up. The base gets hot and dense again. Fusion ignites again. Another nova. Another brilliant flash. Another brief appearance in the sky. And then another long quiet interval while the layer rebuilds. Some nova systems have been observed to recur. T Coronae Borealis, a system about 3,000 light-years from Earth, is a famous example. It erupted as a nova in 1866, and again in 1946, roughly 80 years apart. Astronomers have been watching it closely, expecting another eruption. R.S. Ophiuchi has erupted at least 6 times in the past century, roughly once every 15 to 20 years. These recurrent novae are white dwarfs that are accreting material relatively quickly. So the hydrogen layer builds up fast, and the detonation cycle repeats on human timescales. Here's what makes novae important for our story. Each nova blows away most of the accreted hydrogen, but not necessarily all of it. And even the novae that eject more mass than was accreted can still leave the core slightly altered. The gravitational compression during accretion, the heating at the base of the hydrogen layer, the settling of processed material, all of these contribute to a gradual increase in the white dwarf's core temperature and mass over many nova cycles. The white dwarf is not the same after 1 million years of accretion and periodic novae as it was at the beginning. It is slightly more massive. Its core is slightly hotter. It has inched a tiny bit closer to the Chandrasekhar limit. And there is something deeply unsettling about this. The novae are warning shots. They are bright, visible, dramatic events that astronomers can see from thousands of light years away. They look violent. They look dangerous. But they are not the real threat. The real threat is happening silently, invisibly, deep inside the core where no telescope can see. The core temperature is climbing. The carbon is getting closer to its ignition point. And the novae, spectacular as they are, do absolutely nothing to prevent it. Each one is a distraction, a surface spectacle, while the true catastrophe builds in silence below. With each new layer of accreted material, the white dwarf becomes slightly more massive. Its gravity strengthens slightly. Its interior is compressed slightly more. The electrons inside are packed a little tighter, pushed into slightly higher energy states. The degeneracy pressure increases to match, and for a while, everything remains in balance. But the mass is climbing. Slowly, inexorably, it is climbing. And with every fraction of additional mass, the white dwarf edges closer to the Chandrasekhar limit, closer to the threshold where degeneracy pressure can no longer hold. Now remember the broken thermostat. As mass accumulates on the white dwarf's surface, the weight of the new material compresses the layers beneath it. The interior temperature rises, heated by gravitational compression and by the energy released as accreted material settles. In a normal star, this heating would cause expansion, which would cool things down. But this is not a normal star. This is degenerate matter. The temperature rises and nothing expands. The pressure does not increase to push the material outward. The heat just accumulates. The interior gets hotter and hotter while the structure of the star remains essentially unchanged. The electrons don't care about the heat. They are held in their quantum states by the exclusion principle, indifferent to temperature, responding only to density. And deep in the core of the white dwarf, where the pressure and temperature are highest, where the carbon and oxygen nuclei are packed together at unimaginable densities, those climbing temperatures are approaching a critical threshold. Remember the fuel we talked about earlier? The carbon and oxygen ash left behind when the original star died. That fuel could never ignite when the star was alive because the core was not hot enough. Carbon fusion requires temperatures above 500 million degrees. The original star could not reach those temperatures in its core. But now, in the white dwarf, with mass piling on from above, with gravitational compression intensifying, with no expansion to bleed off the accumulating heat, the temperature is climbing toward that threshold. Not over seconds or minutes, over thousands of years, maybe millions of years. The process is gradual, almost imperceptible, but the direction is unmistakable. The temperature is going up, the structure is not responding, and the carbon sitting in the core, carbon that has been inert for billions of years, carbon that everyone assumed was permanently spent fuel, dead ash, cosmically useless, is getting closer and closer to its ignition point. And then, something subtle but critically important begins to happen. Long before the final catastrophe, long before the runaway that will destroy the star, carbon fusion actually starts. Not explosively, not violently, just barely. A trickle, a few carbon nuclei here and there in the hottest regions at the very center, occasionally collide with enough energy to fuse. The rate is vanishingly small. The energy output is negligible compared to the thermal energy already stored in the core. But it is not zero. Carbon is fusing. Astrophysicists call this phase carbon simmering, and it is one of the most eerie stages in the life of a doomed white dwarf. The core is not yet exploding. It is not even burning in any conventional sense. It is simmering, like a pot of water on a stove that has not yet reached a full boil, but is producing a few occasional bubbles rising from the bottom. This simmering phase lasts for roughly 1,000 years. During that time, the tiny amount of energy released by the scattered carbon fusion reactions is enough to drive slow convective currents in the core. Hot material rises, cooler material sinks, the core stirs. These convective motions are not violent, they are gentle, languid movements of dense, degenerate matter circulating over years and decades. But they are important because they redistribute heat within the core. They determine which regions are hottest, which regions are closest to the ignition threshold, and critically they influence where the final explosive ignition will begin. The simmering core is setting the stage for its own destruction. The convective flows are arranging the temperature profile, sculpting the internal landscape, determining whether the final ignition will occur at one single point near the center, or at several points simultaneously, or slightly off-center in one particular region. These details matter enormously because they determine how the burning front will propagate through the star once the real explosion begins. The geometry of the initial ignition shapes the entire character of the explosion that follows. And throughout this 1,000-year simmering phase, on the surface, the white dwarf looks exactly the same as it always has. A faint, dim, unremarkable point of light. If you were watching it through a telescope, you would see nothing unusual. No flickering, no brightening, no sign that anything is wrong. The star betrays nothing. The catastrophe building inside is completely invisible from the outside. Only the physics knows what is coming. There is a terrible inevitability to this process. The white dwarf is trapped. It cannot shed the accumulating mass. Its companion keeps feeding it material. The mass keeps growing. The interior keeps heating. The thermostat that could save it does not exist. The simmering intensifies year by year, century by century. The convective currents grow stronger. The central temperature creeps higher. Everything is building toward a moment where the temperature at the center of the white dwarf finally crosses the threshold for sustained, explosive carbon fusion. And when that happens, when the simmering pot finally boils over, when the first carbon nuclei begin to fuse in earnest deep in the heart of a degenerate star, the outcome will be unlike anything that happens inside a normal star. In a normal star, carbon ignition is manageable, the star adjusts, it expands, it cools, it finds a new equilibrium and continues burning. But a white dwarf cannot adjust. It cannot expand. The matter is degenerate. The thermostat is broken. When carbon ignites inside a white dwarf, the energy from fusion pours into the surrounding material. The temperature skyrockets. And because the pressure does not increase in response to the temperature, the material does not expand. The density stays the same. The fuel stays packed tightly together, and hotter material fuses faster, much faster, exponentially faster. The hotter it gets, the faster it burns. The faster it burns, the hotter it gets. There is no break. There is no cooling mechanism. There is no expansion to slow the reaction down. The fusion rate increases without limit, feeding on itself in a runaway chain reaction that builds from a flicker to an inferno in a matter of seconds. This is thermonuclear runaway. This is what happens when ignition occurs the wrong way, inside matter that cannot regulate its own temperature. The star does not adjust. It does not find balance. It does not survive. It detonates. And the explosion that follows is one of the most violent events in the entire observable universe. An event so bright, so energetic, and so profoundly important to our understanding of the cosmos that it rewrote the history of modern astronomy. But to understand how that detonation unfolds, how the burning propagates through the star, and what it leaves behind, we need to follow the physics into those final catastrophic seconds when billions of years of quiet stability are erased in a flash brighter than an entire galaxy. The moment arrives without warning. Deep inside the white dwarf, in a region perhaps no larger than a small room, the temperature crosses a threshold that has not been reached in billions of years. Carbon nuclei, packed together at densities 1,000,000 times greater than anything on Earth, begin to fuse. 2 carbon-12 nuclei slam together and merge, producing heavier elements: neon, magnesium, sodium, depending on the specific collision. Each fusion reaction releases energy, and that energy pours directly into the surrounding degenerate material. In a normal star, this is where the thermostat would kick in. The energy would heat the gas would expand, the expansion would cool the material and slow the fusion rate. Balance would be restored within seconds. The star would adjust and carry on burning at a steady, manageable pace. But this is not a normal star. This is a white dwarf. And inside a white dwarf, the matter is degenerate. Electron degeneracy pressure, the force holding the star up, does not respond to temperature. When that first burst of fusion energy heats the surrounding carbon, the pressure does not increase. The material does not expand. The density does not drop. Nothing changes structurally. The carbon is still packed just as tightly as it was a moment ago. The fuel is still sitting right there, compressed together at the same extraordinary density, waiting to be burned. And now it is hotter. Hotter degenerate matter fuses faster. This is the key to everything that follows. Nuclear fusion rates are extraordinarily sensitive to temperature. The relationship is not linear. It is not even gently exponential. For carbon fusion in degenerate conditions, the rate of energy production increases roughly as the 12th power of the temperature. That means if the temperature doubles, the fusion rate increases by a factor of roughly 4,000. If the temperature triples, the fusion rate increases by a factor of over 500,000. These are not gentle increases. These are runaway increases, explosive increases, the kind of increases where a small change in conditions produces an enormous change in outcome. So here is what happens in the first fraction of a second after carbon ignites inside the white dwarf. The initial fusion reactions release energy. That energy heats the surrounding material. The heated material fuses faster. The faster fusion releases more energy. That additional energy heats the material even further. The hotter material fuses even faster still. More energy, more heat, more fusion, more energy. The cycle feeds on itself, each loop amplifying the one before it. The temperature does not climb gradually. It does not rise in a steady, predictable curve. It accelerates. It doubles, then doubles again, then doubles again, each doubling happening faster than the last. Within moments, the temperature in the ignition region soars from hundreds of millions of degrees to billions of degrees. And through all of this, the star does not expand. The material does not move. The density does not change. The thermostat that could slow this process, that could buy time, that could give the star any chance of surviving, simply does not exist. The white dwarf sits there, structurally rigid, held in place by degeneracy pressure, while a thermonuclear inferno builds inside it at a rate that defies easy comprehension. This is thermonuclear runaway. It is perhaps the most violent feedback loop in all of physics. And once it begins, there is no stopping it. There is no mechanism inside the white dwarf that can intervene. There is no circuit breaker, no pressure release valve, no emergency shutdown. The laws of physics inside degenerate matter simply do not permit the kind of self-correction that keeps normal stars alive. The fusion will continue to accelerate until one of two things happens. Either the temperature becomes so extreme that the degeneracy is finally broken and the material can at last expand, or the star is destroyed completely. In practice, both things happen. But by the time the degeneracy breaks, it is far too late. Let me explain what I mean by that. Remember, degeneracy pressure depends on density, not temperature. But there is a limit. If the temperature becomes high enough, if the thermal energy of the particles becomes comparable to the energy associated with degeneracy, then the material transitions out of the degenerate state and starts behaving like normal gas again. At that point, pressure does become temperature dependent. The material can finally expand. But consider when this transition happens. By the time thermal energy matches degeneracy energy in the ignition zone, the temperature has already reached billions of degrees. Carbon fusion has already released catastrophic amounts of energy. The fusion front has already begun spreading through the star. The transition out of degeneracy does not save the white dwarf. It is like a dam breaking after the reservoir behind it has already filled to 1,000 times its capacity. The water is coming through regardless. The dam breaking just means there is nothing left to contain it. Now, let's talk about how the burning actually spreads through the star, because this is one of the most complex and fascinating problems in all of astrophysics. And it is a problem that scientists have been struggling with for decades. When carbon first ignites, it does so in a relatively small region near the center of the white dwarf. The ignition might begin at a single point or at several points roughly simultaneously. The exact geometry of the initial ignition is still debated. It depends on turbulent motions in the core, on subtle temperature variations, on the convective flows that were stirring the interior during the simmering phase that preceded the explosion. The 1,000 years of gentle circulation determined where the hottest spots would be. And those hottest spots are where the match finally strikes. But regardless of where precisely it starts, the burning must then propagate outward through the rest of the star. And the way it propagates determines the nature and the power of the explosion. There are two fundamentally different ways a burning front can move through material. The first is called deflagration. In a deflagration, the burning front moves through the fuel at less than the speed of sound in the material. The energy from the burning zone is transmitted to the unburned fuel ahead of it through thermal conduction. Heat diffuses forward, raising the temperature of the adjacent material until it too reaches its ignition point, and then that material burns, releasing more heat that diffuses further forward. The front creeps through the fuel, burning it layer by layer. A common everyday example of a deflagration is the flame on a candle or the burning of a log in a fireplace. The flame is a deflagration front. It moves through the fuel relatively slowly, at speeds well below the speed of sound. You can watch it advance. You can see the fuel being consumed progressively. The second type of burning is called detonation. In a detonation, the burning front moves through the fuel faster than the speed of sound. It is driven not by thermal conduction, but by a shock wave. The shock wave compresses and heats the fuel ahead of it to ignition temperature almost instantaneously. The burning happens right behind the shock front, releasing energy that sustains and strengthens the shock. A detonation is far more destructive than a deflagration because the energy is released almost simultaneously across a large volume. An everyday example of a detonation is the explosion of dynamite or other high explosives. When dynamite detonates, the burning front races through the explosive material at speeds of several thousand meters per second, far faster than the speed of sound. The energy is released so quickly and so violently that it creates a powerful blast wave. Inside an exploding white dwarf, both of these processes occur, and the transition between them is one of the most important and most poorly understood aspects of the explosion. Current models suggest that the burning begins as a deflagration. Carbon ignites near the center, and the burning front moves outward subsonically, consuming carbon and oxygen and converting them into heavier elements. But here is what makes this deflagration extraordinary. The speed of sound inside a white dwarf is not like the speed of sound in air. In degenerate matter at the densities found in a white dwarf core, roughly 1 billion kilograms per cubic meter, the speed of sound is thousands of kilometers per second. A deflagration moving at a significant fraction of that speed is still incredibly fast by any normal standard, but it is slower than the sound speed, which means the material ahead of the burning front has time to respond to the pressure changes. Information about what is happening can travel ahead of the flame. This matters because it allows the unburned material to begin adjusting before the flame reaches it. The star can start to expand, at least in the regions where degeneracy has been broken by the extreme temperatures. But the expansion is uneven. The burning is not perfectly spherical. The deflagration front is unstable. It develops wrinkles and fingers and mushroom-shaped plumes driven by a phenomenon called the Rayleigh-Taylor instability. Here's what that means. Behind the burning front, the material has been heated to extreme temperatures. It is hot, buoyant, and wants to rise outward. Ahead of the burning front, the material is cooler and denser. This is a gravitationally unstable configuration. Hot, light material underneath cold, heavy material. It is like holding a layer of warm water beneath a layer of cold water. The warm water wants to rise and the cold water wants to sink. The interface between them becomes unstable and develops complex, turbulent structures. Inside the exploding white dwarf, this instability causes the deflagration front to become wildly convoluted. Instead of a smooth, spherical flame sweeping outward, the front develops enormous fingers of burning material that shoot outward into unburned fuel, while streams of unburned material plunge inward toward the center. The surface area of the burning front increases dramatically. More surface area means more fuel is being burned simultaneously. The total energy release accelerates even as the flame's speed itself remains subsonic. This turbulent deflagration phase lasts about 1 to 2 seconds. And during that time, the star is not simply burning fuel into one product. It is running through a chain of nuclear reactions that depend on the local density and temperature, and those conditions vary enormously at different depths inside the star. The result is a layered transformation, like an onion being rewritten from the inside out. In the very center, where the density is highest and the temperatures reach 5 billion degrees or more, the burning is so intense and so complete that it pushes the nuclear reactions all the way to their ultimate endpoint. Carbon fuses into neon and magnesium. Then neon itself captures particles and breaks apart, producing more oxygen and magnesium in a process called neon burning. Then oxygen fuses with oxygen, producing silicon and sulfur. And then silicon burns, building heavier nuclei step by step through a rapid cascade of reactions until the material reaches the ion group elements. The final product in these hottest, densest regions is primarily nickel-56, an unstable isotope of nickel that sits at the peak of the nuclear binding energy curve. At this point, the material has reached nuclear statistical equilibrium. The reactions have gone as far as they can go. No more energy can be extracted. The ash is nickel-56, and it will play a crucial role in the aftermath. But farther out from the center, conditions are less extreme. The density is lower. The temperatures are high, but not as extreme. The burning front arrives and ignites the carbon, but the reactions do not run all the way to the ion group. They stop part way. In these intermediate layers, the dominant products are silicon-28, sulfur-32, and argon. These are called intermediate mass elements, and they form a thick shell surrounding the nickel-rich core. The star's midsection is being converted into silicon and sulfur, while its heart becomes nickel and iron group elements. Still farther out, in the outermost layers where the density is lowest and the burning front arrives last and weakest, the nuclear reactions barely progress beyond the initial stages. Carbon and oxygen fuse partially, producing calcium, magnesium, and some oxygen. These outer regions are not completely burned. Some carbon and oxygen survive unprocessed, blasted outward as part of the debris without ever reaching their fusion threshold. The result is that the exploding white dwarf develops a layered chemical structure during those few seconds of burning. Nickel and iron group elements at the center, silicon and sulfur in the middle layers, calcium and magnesium farther out, and traces of unburned carbon and oxygen at the very edge. This onion-like structure is not just a theoretical prediction. It is directly confirmed by observations. When astronomers take spectra of these explosions at different times, they see different elements appear as the expanding debris becomes transparent layer by layer from the outside in. The outermost fastest moving layers become visible first, showing calcium and silicon absorption features. As weeks pass, the slower inner layers become visible, revealing the iron group elements at the core. The explosion is peeling itself open like an onion, and astronomers can read the chemical layers one by one. But 1 to 2 seconds in, something changes. The deflagration front, which has been accelerating and becoming increasingly turbulent, undergoes a transition. It becomes a detonation. The burning front accelerates past the local speed of sound, and a shockwave forms. This shockwave races outward through the remaining unburned material, compressing it and heating it to ignition temperature almost instantaneously. The entire outer portion of the star is consumed in a wave of nuclear burning that sweeps through the remaining fuel at speeds of 10,000 to 20,000 kilometers per second. This deflagration to detonation transition is one of the most studied and most debated aspects of white dwarf explosions. How exactly does a subsonic flame become a supersonic detonation? The physics is complex and involves turbulence, shock formation in the uneven flow of material, and the interaction between the burning front and the expanding star. Different research groups have proposed different mechanisms. Some suggest the transition happens when the turbulent flame reaches a region of sufficiently low density that the conditions for detonation are met. Others propose that the interaction between the flame and the stellar structure creates localized shock waves that can trigger detonation. The precise mechanism is still an active area of research, But the outcome is clear. Once the detonation begins, the remaining fuel is consumed almost instantaneously. The energy released is colossal. In the span of about 10 seconds from the initial carbon ignition to the final consumption of the outermost layers, the white dwarf releases roughly 1 to 2 times 10 to the 44 joules of energy. That number probably means very little on its own, so let me put it in perspective. The Sun produces about 3.8 times 10 to the 26 joules of energy per second. That is its total luminosity, the amount of energy it radiates in every direction every second. It is enough to power all of human civilization billions of times over. The energy released by an exploding white dwarf in those 10 seconds is roughly equivalent to the total energy our Sun will produce over its entire 10 billion year lifetime. The entire energy output of the Sun, from its birth to its death, released in about 10 seconds. Or consider it another way. The energy released is roughly 1% of the rest mass energy of the white dwarf itself. 1% of the total energy contained in the matter of the star, as described by the equivalent of mass and energy. That sounds like a small percentage, but the total mass of the star is roughly 1.4 times the mass of the Sun. 1% of the rest mass energy of that much material is a number so large that it dwarfs any other energy source in the universe except for gamma ray bursts and the total output of active galactic nuclei. And all of that energy is released in seconds. Not years, not millennia, seconds. The energy is more than enough to completely unbind the star. Gravitational binding energy is the amount of energy required to disassemble an object entirely, to take every particle and move it infinitely far away from every other particle. For a white dwarf near the Chandrasekhar limit, the gravitational binding energy is roughly 3 to 5 times 10 to the 43 joules. The thermonuclear energy released during the explosion exceeds this by a factor of roughly 3 to 5. There is far more energy being produced than is needed to hold the star together. The result is total destruction. The white dwarf does not just explode, it is completely unbound. Every atom that was part of the star is blasted outward into space at tremendous velocities. The outermost layers, which were the least tightly bound, are ejected at speeds of 20,000 to 30,000 kilometers per second. That is roughly 6 to 10% of the speed of light. Even the innermost material, the heaviest elements forged in the hottest, densest regions, is moving outward at thousands of kilometers per second. And here is the detail that distinguishes this explosion from almost every other type of stellar death. There is no remnant. Nothing is left behind. When a massive star explodes as a core collapse supernova, the outer layers are blasted away, but the core survives as a neutron star or a black hole. There's something left at the center. A compressed, incredibly dense object that carries forward some trace of the star that once existed. But when a white dwarf detonates, the explosion is thermonuclear, not gravitational. The energy comes from fusion, not from the collapse of the core. And that energy is more than sufficient to overcome the gravitational binding of the entire object. There is nothing holding anything together anymore. The star is converted entirely into an expanding cloud of extremely hot, extremely fast-moving debris. If you could somehow return to the location of the white dwarf a few hours after the explosion and look for it, you would find nothing. No neutron star, no black hole, no dense remnant of any kind. Just an expanding shell of gas and dust, flying outward in every direction, carrying with it the newly forged elements that were created in those final violent seconds. This is what makes white dwarf explosions fundamentally different from any other type of stellar explosion. A core collapse supernova is violent, but something survives. It is like a building demolished by a wrecking ball. The building is destroyed, but the foundation is still there. The rubble is piled around the base. There's evidence of what once stood at that spot. A white dwarf explosion is different. It is like the building being vaporized. Not just knocked down, but erased. The foundation gone. The rubble gone. The ground it stood on gone. The atoms that made up the building scattered across the countryside. Nothing remains to mark the spot where the star once existed. Think about what that means for a star that might have been sitting quietly in space for 5 or 6 billion years. A white dwarf that formed when the universe was young. That cooled slowly through cosmic epoch after cosmic epoch, surviving the formation of planetary systems, the evolution of life on nearby worlds, the rise and fall of civilizations that might have looked up at it in their night sky as a faint, unremarkable point of light. Billions of years of quiet existence, erased in 10 seconds. The star that was there for longer than most things in the universe have existed simply ceases to be. And the explosion is not gentle. The expanding debris plows into the surrounding interstellar medium, sweeping up gas and dust, creating a vast expanding shell called a supernova remnant. This shell can persist for tens of thousands of years, gradually slowing and cooling, and eventually merging back into the interstellar medium. But even as it fades, the elements it carries, the nickel and iron and silicon and calcium forged in those final seconds, are being dispersed into the galaxy, mixed into the clouds of gas and dust that will one day collapse to form new stars and new planets. There is another subtlety to the explosion that is worth understanding, because it connects to one of the most important uses of white dwarf explosions in all of modern astronomy. And that is the question of uniformity. Not all stellar explosions are the same. Core collapse supernovae, the type caused by the death of very massive stars, vary enormously in brightness. Some are relatively faint. Others are extraordinarily luminous. The brightness depends on the mass of the original star, the composition of its outer layers, the amount of radioactive material produced, and many other factors. No two core collapse supernovae are exactly alike. They are messy, complicated, individual events, but white dwarf explosions are different. They are remarkably uniform. And the reason traces directly back to the Chandrasekhar limit. Every white dwarf that explodes in this manner is doing so because it has reached approximately the same mass, roughly 1.4 solar masses. The amount of fuel available is approximately the same in each case. The density and temperature conditions at ignition are approximately the same. The nuclear reactions that occur are approximately the same. The total energy released is approximately the same. This does not mean every white dwarf explosion is identical. There are variations. The exact composition of the white dwarf matters. The metallicity of the original star affects the ratio of carbon to oxygen in the core. The precise details of the deflagration to detonation transition introduce some variability. The geometry of the ignition, whether it begins at a single point or at multiple points, affects how the burning front evolves. And there are actually different physical scenarios that can bring a white dwarf to the point of explosion. In some cases, the white dwarf slowly accretes matter from the companion as we have described. In other cases, Two white dwarfs in a tight binary system spiral toward each other, losing energy through gravitational wave emission over millions of years until they merge. If the combined mass exceeds the Chandrasekhar limit, the merger can trigger the same kind of thermonuclear runaway. The details differ, but the outcome is similar. Despite these variations, the overall brightness of white dwarf explosions clusters around a relatively narrow range. When astronomers measure the peak luminosity of these events, they find that most of them fall within a fairly tight distribution. And crucially, the small variations that do exist are correlated with other observable properties, particularly the rate at which the brightness fades after the peak. Brighter explosions tend to fade more slowly, dimmer ones fade more quickly. By measuring how quickly the light declines after the peak, astronomers can determine how intrinsically bright the explosion was, even if it occurred in a distant galaxy where the distance is not directly known. But how do astronomers know they are even looking at a white dwarf explosion and not some other type of stellar event? This is where spectroscopy becomes essential. When astronomers split the light from an explosion into its component wavelengths using a spectrograph, they see a pattern of bright and dark features that acts like a chemical fingerprint. Different elements absorb and emit light at specific wavelengths, and by reading these features, astronomers can determine what the expanding debris is made of. A white dwarf explosion has a very distinctive spectral signature. The most prominent feature near peak brightness is a deep absorption trough caused by silicon. Specifically, silicon-28 absorbs light at a characteristic wavelength that gets shifted and broadened by the tremendous velocities of the expanding debris. This silicon absorption feature is the single most important identifier. It is what defines the Type 1a classification. If an astronomer sees a supernova with a strong silicon absorption feature near peak brightness, they know they are almost certainly looking at an exploding white dwarf. Equally important is what the spectrum does not show. In a white dwarf explosion, there are no hydrogen features in the spectrum, none at all. This makes a perfect sense when you remember what a white dwarf is. It is a carbon-oxygen core. The hydrogen was shed long ago when the star's outer layers were expelled during the planetary nebula phase. By the time the white dwarf explodes, it contains virtually no hydrogen. A core collapse supernova, by contrast, usually shows strong hydrogen features, because the massive star still had its hydrogen envelope when it exploded. The absence of hydrogen and the presence of silicon together form the definitive signature of a white dwarf explosion. No other type of stellar event produces this particular combination. There is also something interesting happening at the edges of the Type 1a classification. Not all white dwarf explosions are perfectly normal. Some are slightly peculiar. A subclass designated after the event SN 1991T is overluminous. These explosions are brighter than typical, fade more slowly, and show weaker silicon features. They may result from white dwarfs that were slightly more massive than average, or from explosions where a greater fraction of the star was burned to nickel 56. On the other end, a subclass designated after SN 1991 BG is subluminous. These are dimmer, fade faster, and show stronger features from intermediate mass elements like titanium. They may result from less complete burning, where less nickel 56 was produced, and more material was left as intermediate elements. These subtypes test the boundaries of the standard model, but they also reinforce it. Even the outliers follow predictable patterns. The brighter slower and dimmer faster correlation holds across the entire range. The physics is consistent even when the details vary. And this consistency, this predictable behavior across thousands of observed events in galaxies spanning billions of light years, is what makes white dwarf explosions so powerful as distance markers. This relationship between peak brightness and fade rate is extraordinarily powerful. It means that white dwarf explosions can be calibrated. If you know how bright the explosion truly was, and you can measure how bright it appears from Earth, the difference tells you how far away it is. The dimmer it appears, the farther away it must be. It is the same principle you use when you see a car's headlights at night. You know roughly how bright headlights are. If they appear faint, the car is far away. If they appear bright, it is close. White dwarf explosions are the headlights of the universe, standard candles, objects of known intrinsic brightness that can be used to measure distances across cosmic scales. And these are not dim headlights. These explosions are so bright that they can be seen billions of light years away. A single exploding white dwarf can briefly outshine every star in its host galaxy combined. For a few weeks, one dying star produces more light than hundreds of billions of living stars. This makes them visible at extraordinary distances, far deeper into the universe than almost any other individual object. This property, this combination of enormous brightness and remarkable uniformity, turned white dwarf explosions into one of the most important tools in observational cosmology. They became the yardstick by which astronomers measure the expansion of the universe itself. And what that yardstick revealed in the late 1990s shook the foundations of physics and cosmology in a way that no one anticipated. A discovery so startling and so important that it earned the Nobel Prize, reshaped our understanding of the cosmos, and raised questions that remain unanswered to this day. The destruction of a white dwarf, a dead star igniting the wrong way, turned out to illuminate far more than just itself. It illuminated the fate of the entire universe. For most of the 20th century, cosmologists believed they understood the broad outline of the universe's fate. The universe was expanding. Edwin Hubble had demonstrated that in 1929 by showing that distant galaxies were receding from us, and the farther away a galaxy was, the faster it was moving. This expansion had been set in motion by the Big Bang roughly 13.8 billion years ago, and ever since, the universe had been growing larger. The question that remained was what would happen next. Gravity, the attractive force between all matter, should be slowing the expansion down. Every galaxy in the universe is pulling on every other galaxy. Over time, this mutual gravitational attraction should act like a brake, gradually decelerating the expansion. The big question was whether gravity would eventually halt the expansion entirely and reverse it, causing the universe to collapse back on itself in a big crunch, or whether the expansion would slow but never quite stop, continuing forever but at an ever-decreasing rate. To answer this question, astronomers needed to measure how the expansion rate had changed over time. They needed to look at objects very far away, objects whose light had been traveling for billions of years, and compare their distances and velocities to objects closer to us. If the expansion was decelerating, as almost everyone expected, distant objects would be slightly closer than you would predict from a constant expansion rate. The universe would be decelerating, and the distant objects would show the fingerprints of that slowdown. This is where white dwarf explosions became indispensable. As we discussed, These events are remarkably uniform in brightness. They can be calibrated by measuring how quickly their light fades after peak brightness, and they are extraordinarily luminous, visible at distances of billions of light years. They are the perfect cosmic yardstick for measuring vast distances across the universe. In the 1990s, two independent research teams set out to use white dwarf explosions to measure the deceleration of the universe. One team was led by Saul Perlmutter at the Lawrence Berkeley National Laboratory. The other was led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins University. Both teams were looking at white dwarf explosions in distant galaxies, measuring their brightness and comparing it to their redshift, which tells you how much the universe has expanded since the light was emitted. They expected to find that the distant explosions were slightly brighter than they would be in a uniformly expanding universe. That would mean the distant galaxies were closer than expected, which would mean the expansion had been faster in the past and was now slowing down. Deceleration, gravity winning, the expected result. But that is not what they found. Both teams, working independently with different telescopes, different data sets, and different analysis methods, found the opposite. The distant white dwarf explosions were fainter than expected. Not brighter, fainter. This meant the distant galaxies were farther away than they should have been. The expansion of the universe was not slowing down. It was speeding up. The universe's expansion is accelerating. When the teams first saw these results, they assumed they had made a mistake. They checked their data. They reanalyzed their observations. They looked for systematic errors, for dust that might be dimming the distant explosions, for some flaw in their calibration method. They found nothing wrong. The result held. The expansion of the universe is not decelerating under the influence of gravity. Something is pushing it to expand faster and faster. Both teams published their findings in 1998. The announcement sent shockwaves through the physics community. It was one of the most unexpected discoveries in the history of science. No mainstream theory at the time predicted accelerating expansion. Gravity pulls things together. It should slow expansion, not speed it up. For the expansion to be accelerating, there had to be some kind of energy pervading all of space, some force pushing the universe apart more strongly than gravity pulls it together. This mysterious energy was given a name, dark energy, and to this day, more than a quarter of a century after the discovery, we still do not know what it is. We know it exists. The evidence is overwhelming and comes from multiple independent observations. Not just white dwarf explosions, but also the cosmic microwave background radiation, the large-scale distribution of galaxies, and other cosmological measurements. All of these observations converge on the same conclusion. Roughly 68% of the total energy content of the universe is dark energy. It dominates the cosmos. It is the single largest component of the universe, and we have essentially no idea what it is. Some physicists think dark energy might be related to what Albert Einstein called the cosmological constant, a term he introduced into his equations of general relativity in 1917 and later called his greatest blunder. Einstein added the cosmological constant to make his equations produce a static universe, which was what everyone believed in at the time. When Hubble discovered the expansion, the cosmological constant seemed unnecessary and Einstein abandoned it. But perhaps he was right after all, just for the wrong reasons. a cosmological constant would produce exactly the kind of accelerating expansion we observe. It would represent a fixed energy density built into the fabric of space itself, a property of empty space that causes it to expand at an ever-increasing rate. Other physicists think dark energy might be something more dynamic, a field that changes over time and might even reverse its effects in the far future. These models go by names like quintessence, and they predict a universe whose fate might be very different from the one implied by a simple cosmological constant. Still, others suggest that our understanding of gravity itself might be incomplete, that general relativity might need to be modified on the larger scales, and that what we are calling dark energy is actually a sign that our theory of gravity is wrong. We do not know which of these explanations is correct. We might not know for decades, but the discovery itself, the discovery that the universe's expansion is accelerating, came directly from the study of exploding white dwarfs. Dead stars that ignited the wrong way, stars that destroyed themselves in thermonuclear catastrophe, became the tools that revealed the deepest secret of the cosmos. Without white dwarf explosions and their remarkable uniformity, we might still not know that dark energy exists. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for their discovery. But the prize really belongs to the physics itself, to the bizarre chain of events that begins with a dead star quietly cooling in the darkness, gains mass from a companion, crosses a threshold its internal physics cannot handle, and detonates so brightly and so consistently that astronomers can use it to measure the expansion of the universe across billions of light years. It is one of the most extraordinary connections in all of science. The death of a single small star illuminating the fate of the entire cosmos. Now let us turn to what the explosion actually leaves behind. Not at the site of the star itself, because as we discussed, nothing remains there. No remnant, no core, no compressed object of any kind. The star is completely unbound. But the debris, the material that is blasted outward, that debris is extraordinarily important because it is carrying something precious, elements, freshly forged elements that did not exist before the explosion, elements that the universe desperately needs. During those final seconds of thermonuclear burning, the white dwarf's carbon and oxygen were converted into a range of heavier elements. The specific products depend on the density and temperature at which the burning occurred. In the densest, hottest regions near the center, where temperatures exceeded 5 billion degrees, the dominant product is nickel-56. This is an unstable isotope of nickel. It is radioactive, and its decay is going to be very important in a moment. In regions of somewhat lower density and temperature, the burning produced silicon-28, sulfur, and argon. In the outermost layers, where conditions were less extreme, the burning produced calcium, magnesium, and oxygen. The total amount of nickel-56 produced in a typical white dwarf explosion is roughly 6/10 to 8/10 of a solar mass. Think about that. More than half the mass of our entire sun converted into a single radioactive isotope during a 10-second explosion. This is an astonishing quantity of nuclear synthesis, accomplished in moments, and it is the nickel-56 that powers the visible light we actually see from the explosion. Here is how that works. In the first few days after the detonation, the expanding debris is opaque. It is so dense and so hot that light cannot escape from it. The photons generated by the explosion bounce around inside the expanding cloud, absorbed and re-emitted countless times. From the outside, the event initially appears relatively dim because the light is trapped inside the debris. But the debris is expanding at tens of thousands of kilometers per second. As it expands, it thins out. As it thins, it becomes more transparent. Photons can escape more easily. The brightness increases. Over the course of roughly 2 to 3 weeks after the explosion, the expanding debris becomes transparent enough that light can stream out, and the event reaches its peak brightness. But here is the key question. What is generating that light? The thermonuclear explosion itself lasted only seconds. The fusion energy was released in those few violent moments. If the only source of light were the initial explosion energy, the debris would simply cool and fade as it expanded. The event would brighten briefly as the debris became transparent and then dim rapidly as the thermal energy was radiated away and diluted by the expansion. That is not what happens. The light curve of a white dwarf explosion has a distinctive shape. It rises to a peak over about 2 to 3 weeks, and then declines, but it declines slowly, much more slowly than you would expect if the only energy source were the initial explosion. Something is continuing to pump energy into the debris long after the explosion itself is over. That something is the radioactive decay of nickel-56. Nickel-56 is unstable. It decays into cobalt-56 with a half-life of about 6.1 days. The cobalt-56 is also unstable. It decays into iron-56 with a half-life of about 77 days. Both of these decay processes release energy in the form of gamma rays. Those gamma rays are absorbed by the surrounding debris and converted into heat, which is then re-radiated as visible light. So the light you see from a white dwarf explosion weeks and months after the event is not light from the explosion itself. It is light generated by radioactive decay. The nickel-56 acts like a slow-release energy source, steadily converting nuclear energy into thermal energy over weeks and months, keeping the debris glowing long after the initial detonation has ended. The peak brightness of the explosion corresponds roughly to the moment when the debris has become transparent enough to release the light being generated by nickel decay, and the slow decline after the peak follows the decay rate of first nickel-56 and then cobalt-56. This is beautifully confirmed by observations. When astronomers measure the light curves of white dwarf explosions, the rate at which the brightness declines after the peak matches almost perfectly the predicted decay rates of nickel-56 and cobalt-56. The physics is clean, elegant, and well understood. Radioactive decay, one of the most precisely measured processes in all of physics, is powering the light we see from exploding white dwarfs billions of light years away. And the final product of all this decay, iron-56, is stable. It does not decay further. It just sits there in the expanding debris cloud, mixed with silicon and calcium and sulfur and all the other elements forged in the explosion, drifting outward into the interstellar medium at thousands of kilometers per second. Over thousands of years, the debris slows down as it sweeps up surrounding gas. It mixes into the interstellar medium. It becomes part of the vast clouds of gas and dust that pervade the galaxy. And eventually, millions or billions of years later, those clouds collapse under their own gravity to form new stars and new planetary systems. And the elements from the dead white dwarf are incorporated into those new systems, into the new star, into the planets that form around it, into the rocks and oceans and atmospheres of those planets. This is where the story becomes personal, because those elements are inside you right now. The iron in your blood, the element that allows hemoglobin to carry oxygen from your lungs to every cell in your body, was almost certainly forged in the explosion of a white dwarf. Not all of it. Core collapse supernovae also produce iron. But white dwarf explosions are among the dominant sources of iron in the universe. The iron atoms circulating in your bloodstream right now were once part of a dead star that ignited the wrong way. A star that sat quietly for billions of years, slowly cooling in the darkness before a cascade of physics it could not control, turned it into one of the most violent events in the cosmos. And the iron that was forged in that violence eventually found its way into a cloud of gas that collapsed to form our solar system, was incorporated into the planet Earth, and 4.5 billion years later ended up inside you. The calcium in your bones tells a similar story. Calcium is produced in the intermediate layers of an exploding white dwarf, where temperatures are high enough to fuse silicon and sulfur, but not quite extreme enough to push the reactions all the way to the iron group. This calcium was blasted into space, mixed into the interstellar medium, and eventually became part of the molecular cloud that gave birth to our sun. It was incorporated into the rocky material that formed Earth. And over billions of years of geological and biological processes, it became part of the skeletal structures that allow you to stand upright. Every bone in your body contains calcium that was forged in the heart of an exploding dead star. Silicon, the element that forms the backbone of rock and sand and glass, is another major product of white dwarf explosions. The silicon in the ground beneath your feet, in the sand on beaches, in the computer chips that power the device you might be using to listen to this right now. Much of that silicon traces back to thermonuclear burning inside degenerate matter. The Earth's crust is roughly 28% silicon by mass, making it the second most abundant element in the crust after oxygen. And a significant fraction of that silicon was produced in events where white dwarfs crossed the wrong threshold and destroyed themselves. Humans have been witnessing these explosions for over 1,000 years without knowing what they were. In the year 1006, astronomers in China, Japan, Iraq, and possibly Europe recorded the appearance of a brilliant new star in the constellation Lupus. It was the brightest stellar event in recorded history, reaching an apparent brightness roughly 16 times brighter than Venus. It was visible during the day for weeks, and remained visible to the naked eye at night for over 2 years. Modern astronomers have identified the remnant of this explosion. It is almost certainly a white dwarf detonation, a Type 1a supernova roughly 7,200 light-years from Earth. In 1572, the Danish astronomer Tycho Brahe observed another brilliant new star in the constellation Cassiopeia. It appeared suddenly in a region of sky where no star had been visible before, grew brighter than Venus, and remained visible for about 16 months. Tycho's meticulous observations of this event, known today as SN 1572, helped challenge the ancient belief that the heavens were fixed and unchanging. Modern analysis of the remnant confirms it was a Type 1a supernova, a white dwarf that detonated roughly 8,000 light-years away. The light from that explosion reached Earth in 1572, and Tycho saw it without understanding what he was witnessing. He saw a star appear where none had been before. What had actually happened was that a dead star, one that had been quietly cooling for billions of years, had finally crossed a threshold and erased itself from existence in a thermonuclear flash. Just 32 years later, in 1604, Johannes Kepler observed another bright new star in the constellation Ophiuchus, known today as SN 1604. This was the last supernova observed in our galaxy with the naked eye, and it too may have been a Type 1a event, though the evidence is less certain than for Tycho's supernova. These historical observations remind us that white dwarf explosions are not abstract theoretical events. They happen. They happen in our galaxy. They happen in galaxies all across the observable universe. Astronomers detect several hundred of them every year in distant galaxies using modern telescopes and survey programs. Each one represents a white dwarf that lost its battle with its own physics. A dead star that accreted too much mass, crossed the Chandrasekhar limit, ignited as carbon in a degenerate core, and was consumed by the runaway burning that followed. Each one also represents a contribution to the chemical evolution of its host galaxy. The elements forged in these explosions are dispersed into the interstellar medium, enriching the raw material from which future generations of stars and planets will form. Over billions of years, the cumulative effect of thousands of white dwarf explosions has fundamentally altered the chemical composition of the Milky Way. The galaxy today contains far more iron, silicon, calcium, and other heavy elements than it did when it was young, and a significant fraction of that enrichment came from dead stars that ignited the wrong way. There's a deep irony in all of this. The most destructive event a white dwarf can experience, the total annihilation of a star that had been stable for billions of years, is also one of the most creative events in the cosmos. Destruction and creation are inseparable. The explosion that erases the star simultaneously forges the elements that life requires. Iron for blood, calcium for bones, silicon for rock. Without these elements, planets like Earth could not exist. Without planets like Earth, life as we know it could not exist. And without white dwarfs igniting the wrong way, many of these elements would never have been produced in the quantities the universe contains today. You exist because dead stars exploded. Not just any explosion. This specific kind of explosion. The kind that happens when degenerate matter ignites and the thermostat is not there to save it. The kind where a quantum mechanical principle that normally provides stability instead enables catastrophe. The kind where 10 seconds of thermonuclear runaway produces more energy than the sun will emit in its entire lifetime and scatters freshly forged elements across light years of space. And here is perhaps the most remarkable part of all. The white dwarf did not choose to explode. It did not fail or malfunction. It simply followed the laws of physics. Electron degeneracy pressure held it up for as long as it could. The Pauli exclusion principle kept the electrons in their states, providing structural support without any need for heat or fusion. The star was doing exactly what physics said it should do. And then mass was added. Slowly. Gradually. And the same physics, the same unbreakable laws, led inexorably to ignition. Carbon fused because the temperature reached the threshold. The temperature reached the threshold because the material could not expand. The material could not expand because degeneracy pressure does not depend on temperature. Every step followed logically, inevitably, from the one before it. The explosion was not an accident. It was a consequence. The direct, unavoidable consequence of degenerate matter being pushed past a limit that the universe itself defined. And from that consequence, from that inevitable catastrophic outcome of physics doing exactly what physics does, came the raw materials for everything. For worlds, for oceans, for the proteins that fold into the machinery of life, for the hemoglobin molecule that carries oxygen through your bloodstream at this very moment, for the bones that hold you upright as you listen to these words. There is something profound in this, something that goes beyond the physics, beyond the mathematics, beyond the careful observations and calculations that allow us to understand how these events work. It is the recognition that the universe builds complexity out of destruction, that the most violent events produce the most essential materials, that a dead star, igniting the wrong way, erasing itself in a flash of thermonuclear fury, is simultaneously performing an act of creation so fundamental that without it, the universe as we know it could not exist. The white dwarf is gone. Billions of years of quiet existence ended in seconds. No remnant, no trace, just an expanding cloud of newly forged elements, drifting outward into the darkness, carrying with it the seeds of future worlds. And somewhere, billions of years later, on a small rocky planet orbiting an ordinary star, a living being made partly of those elements looks up at the night sky and wonders where it all came from. The answer's written in their very atoms, forged in the heart of a dead star that burned the wrong way, and, in doing so, gave the universe everything it needed to make something extraordinary. Thank you for joining me on this journey tonight. If you found this exploration valuable, a like or subscribe would mean a great deal. It helps me keep making these deep dives into the physics of our universe. And the next time you look up at the stars, remember that some of them are white dwarfs, quietly cooling, patiently fading. Most of them will sit there for billions of years without incident, but a few of them, the ones orbiting too close to a companion, the ones slowly gaining mass, are ticking. Not toward death exactly, toward something more absolute than death, toward erasure. And from that erasure will come iron and calcium and silicon and everything the universe needs to start again. Sleep well tonight. The atoms in your body were forged in fire, and the stars that made them are still out there, waiting for their turn to burn the wrong way. Good night.